Jai Hind, everyone. The topic we are going to take today is field due to infinitely long, straight, uniformly charged wire. So, here we are considering a uniformly charged wire which is infinitely long. The wire is infinitely long, both the sides. Okay? Charges are uniformly distributed on the wire. Let us suppose a point P where we need to find the electric field intensity. This point P, we need to find the electric field intensity. So the point at which we need to find the electric field intensity, at that point we used to keep a test charge, and the test charge is always positive in nature. The test charge is always positive in nature. That means this positive and this positive will be repulsive in nature. Okay, let's draw a diagram. Let us draw a straight line passing from there, which shows the repulsive nature. And let us draw a straight line passing from this point, which shows the repulsive nature. If this is your E1 with a vector sign, this is your E2 with a vector sign, then the resultant will be in this direction. It will be marked as E vector resultant. Am I clear? This positive charge will be repulsive in nature with respect to the test charge kept at point P, denoted by E1. This positive charge will always repel this test charge marked as E2, and E2 and E1 will have a resultant which is marked as a E resultant. Okay. Now we do know very clearly that every body which is having a uniform charges around it will be marked with a Gaussian surface. Now in this 2D surface, we can see this wire as a two-dimensional wire. But on a 3D surface, this wire will be look like a cylindrical body. This wire will be look like a cylindrical body. Okay? So, a Gaussian surface will be marked over here in such a way that there will be a denotation of cylindrical body, and this cylindrical body is enclosing all the charges. As per the Gaussian law, the Gaussian surface should enclose the charges. So this Gaussian surface is enclosing these charges. Now cylinder is uniform, a symmetric body, both the ends. This area of cross section should be same. The diagram is a little bit, you can say, non-uniform. You can say this area is greater than this area. But when you draw with your scale and pencil uniformly, then this area and this area will remain uniform. It should remain uniform. And the cylinder is a symmetric body. Okay. So, this is a surface number 1. Let us consider. This is another surface number 2. Now, this one is another surface. As I have given you the example last video, that this is a cylindrical surface. Now if we take a planar on this surface, this is a cylinder, this pen is a cylinder. Okay. If we take a planar on this surface, the planar will be infinitely small. On this curved surface, and will have a normal in the upward direction. Like this, you can say. It will have a normal in this direction. Okay. Hence, if we take an infinitely small area over here, then we can draw a normal in this direction, marked as unit vector n. This is your third surface. When this is the first surface, the normal will be in this direction. This is the second surface, the normal will be in this direction. And this is the third surface, normal is in this direction. Okay. So I hope the diagram is very much clear to you. Okay. Hence, according to Gauss law, we know this very well that closed integral E dot ds will be equals to Q upon epsilon naught. It should be there. But in this case, we have three regions. First surface, first region you can say, second region, second surface you can say, third region or third surface you can say. So when we write for the first surface, so EDS for first surface plus EDS for second surface plus EDS for third surface. E dot ds, we are going to have the vector signs over here. We got the vector signs and whole equal to Q upon epsilon naught. Hopefully I am very much clear about this equation. First surface, second surface and third surface. Now when we break this, we are going to get EDS cos theta, EDS cos theta, EDS cos theta. Am I clear? So if we see, this is the E resultant, this is the unit vector n. So in between E resultant and unit vector n, we will have an angle of 90 degree. Am I clear? E resultant and n vector, we are going to have the angle of 90 degree. E resultant and n vector, we are going to have the angle of 90 degree. But in the third region, when you will see unit vector n and E resultant are acting in the same direction, hence the angle will be 0 degree. In that case, for region 1, if we break this, it should be written as EDS cos 90 degree for region 1 plus EDS cos 90 degree for region 2 plus for region 3 EDS cos 0 degree equals to Q upon epsilon naught. Now we know this very clearly that cos 90 equals to 0, cos 90 equals to 0 and cos 0 degree equals to 1. Hence this part will equals to 0 and we will left with only this part. EDS is equals to